All right. So if you've been following the notes, you have read about how to use how to add vectors using the triangle law or the parallelogram law, right? If we have a vector like this first one and a vector like the second, and we want to add them, one way we can do this is to just put them, head to tail to tip, whatever you want to call that, and we can say then that their vector sum is what you would get if you went from the beginning, the initial point of the first vector, straight to the final point of the second vector. Right? So if this is the vector A and this is the vector B, then here is the sum A plus B. So hopefully, that portion of the text made sense. Maybe you try some of the exercises in WebAssign that are just working with pictures. If you haven't yet, maybe go do that first so you get some intuition of how adding vectors works geometrically. And that's lovely when you have these little pictures. But of course, if you're trying to solve precise physical problems, you probably have, you hopefully have very precise descriptions of the direction of a vector and the length of a vector, and you want to find very precisely the resulting vector, the resultant, for instance, if you're working with force calculations, or net velocity if you're adding velocity vectors, or whatever you're doing. And what you do not want to have to do is like pull out a piece of graph paper. I mean, these days it would be a computer, but in the olden days, you don't want to have to pull out a piece of graph paper and a ruler and very carefully plot out the individual vectors and then measure what happens as a result, right? That's time consuming and there are limitations on precision there. We want to compute it precisely. And of course, from your past studies of trigonometry, you know how to compute these sorts of things precisely. If you have the exact lengths, the magnitudes of the vectors A and B, and you also know their exact directions, for instance, given as angles off of the horizontal or whatever, then you can find the angle between those two vectors. So if you had the length of A and the length of B and the angle between them, you can use law of cosines to find the length of the third side. And once you have that, you can use either further applications of law of cosines or you could use law of sines to then start filling in whatever other angles you want. So, you could find then maybe this angle, and that would let you figure out the precise direction of this vector, right? So that works, but you probably remember that law of cosines is a little bit of a pain. It's nice to avoid it when possible, and that is particularly the case. These are relatively simple situations, but what if you're working in some sort of situation where you have a whole slew of vectors that you are trying to add together, and you do not want to have to do however many applications of the law of cosines just to figure out how to get from here over to there, right? So we would like a much more efficient way of going at this. So to develop that, let me first, we have spoken from the beginning about the magnitude of a vector or the length of a vector. Remember, we just sort of informally defined a vector as a quantity that has both magnitude and direction. Yes, magnitude and direction. And when we draw this, it's difficult to say one thing while writing another, so let me stop writing for a moment. When we draw a vector, we represent the magnitude pictorially with a length. So we typically use the terms magnitude and length interchangeably, right? Length is the geometric concept of how we draw a vector. Magnitude is, what we often get if we're working with a less spatial vector. If you're looking at, if you're talking about a velocity or a force, you don't really want to talk about the length of that, right? You would talk about its magnitude. How strong is that? How high, how fast is the velocity? How strong is the force? So the magnitude or length of a vector v, and I should point out here, since I'm using these, you saw those with a and b and v. I'll remind you that it's very important to make sure you distinguish between the vector and scalar variables. You can do that however you want, but this having some sort of an arrow or half arrow written above is the most common thing. But however you normally write your variables, you don't have to use cursive like I do. This is just how I write my variables. However you normally write your variables, if you just print a vector like v or a or b, like these would be ordinary variables perhaps, and you might want to put little, vector symbols above them to distinguish those. The magnitude or length of a vector v is denoted. We have special symbols for that. And there are actually a couple of common notations that we use. Sometimes we put the vector between single bars, like an absolute value, or we can put the vector between double bars. Right, the single bar notation, like I said, it strongly resembles absolute value, and it's that same basic idea. And in fact, if you're careful with how you represent things, if you think of the real number line as a one-dimensional vector space, and ordinary scalar variables as one-dimensional vectors, then the magnitude of the vector and the absolute value of that number really mean the same thing. So this is a very suggestive notation. Sometimes it is useful to have something more distinct. So we might use this double bar notation, and this double bar is often used with what's called a norm. So if you've ever heard a reference to a norm of something, you may see that reference with a double bar. Both of these notations are in common use. I actually prefer the double bar myself, but Stewart exclusively uses the single bar, or almost exclusively as far as I can tell. So to be as consistent as possible with the textbook, I will stick to the single bar notation to try to avoid confusing anybody. But if you prefer to use the double bar, maybe you have worked with this in past physics classes or something, or maybe you just like how it looks, I absolutely encourage you to use it. I can read it just fine. Feel free to do that. Just WebAssign might not like it, so you'll want to, I suppose that's another reason for me to stick with the single bars, because WebAssign will probably need things entered in with single bars if it ever asks for vector magnitudes. I'm not sure if that comes up. But those are two very common notations for this. Now going back to the importance of distinguishing between vector and scalar values, there is a common convention of denoting the magnitude of a particular vector with the scalar variable that uses the same letter. So if you have a velocity v, its magnitude is a speed, and that speed will usually be written as the scalar v. So again, make sure that every single time you write a vector, you have the some sort of vector notation involved with it. Whether it's, I mentioned this in my notes, you can use the half arrow, you can use a full arrow. Some people put an arrow under the variable, that's much less common. Some people use just a bar above or below. These are slightly more common, but also they clash with other notations, right? The bar is sometimes used to represent an average value or an expected value or something like that. You can use what you want as long as you're consistent, but I do recommend one of the arrow notations as being the least ambiguous. But yes, so we've talked about a magnitude or a length. There's another piece of terminology here. A unit vector has length 1. So this isn't a specific vector, it's just a category of vector. Sort of like when we talk about prime numbers. Some numbers are prime, some numbers are not. Some vectors are unit, most vectors are not. If a vector's magnitude is 1, then we call it a unit vector. If a vector A is not equal to the 0 vector, that's the 0 vector, not the scalar 0, then the unit vector in the direction of A is, now there are a few ways we can write this. So, got a straight, there we go. There's a few ways we can write this. The textbook often calls unit vectors u. Okay? But not every vector called u is a unit vector. So this is a little bit dangerous. You don't want to, this is just kind of an arbitrary thing. We could have called it x here, right? We're just picking a name for the thing. But just because you see u, that doesn't necessarily mean unit vector, right? You have already worked, or you've seen examples in the text and WebAssign, or you will soon if you haven't yet, that have vectors, they have vectors like u, v, and w, for instance, and you have to add these things. And u is not necessarily a unit vector, right? It could be anything. So just because we write a vector u, it doesn't mean it's a unit vector. There is a notation that I'm a little surprised that Stewart doesn't use because it's quite common, but it's not universal. There is a notation where instead of using an arrow symbol for a vector, we sometimes use a circumflex. In a mathematical context, we call this hat for short. It's like the variable is wearing a little hat. So this symbol I would read as u hat. And putting a circumflex over a vector name indicates that it is a unit vector. It's not necessary. The textbook doesn't use it. I don't think WebAssign will interpret it correctly, so don't rely on it too much. It is my habit to use it, so you will see when I'm writing, I'll have these hats on unit vectors. That's just a little reminder. It's just a thing to remind the reader, hey, by the way, remember that this is a unit vector, and that's useful. And if you do use that notation, you can even, now this is dangerous, I don't necessarily recommend doing this too much because having so much information rely on a tiny little symbol is dangerous, but if you have a vector A, you could have a vector A hat that represents the unit vector in the direction of A. So these would be two different things, but associated. Like I said, it is a little bit dangerous. It's up to you if you feel comfortable doing something like that. But whichever way you want to call this, maybe you just call it the vector u. We can, that was a long aside. Let me make that a little bit bigger so you can read that better. Let me explain what I'm doing here, because I went off on a tangent, and some of you probably forgot what I was saying. So suppose we have a non-zero vector A. So there is, let me scroll down and get a little bit more, a little bit of space to work with here. So suppose this is the vector A. Non-zero, so it has a direction. We might be interested in knowing the unit vector in the direction of A. And I say might be, there are actually many places where we do use this. So suppose, for example, that A has length 3, just for the sake of illustration. So if the length of A is 3, then we might have something like that. Could be a unit vector in the same direction as A. Same direction as A. I tried to draw that approximately parallel, and about 1/3 the length. That would be 1/3 A, right? From the way scalar multiplication works. Here's a vector A, here's 1/3 of A. So if A was 3 units long, 1/3 A is 1/3 as long. This is only 1 unit long then. So this would be a unit vector. So that's what we're expressing here. Remember that the magnitude of a vector is going to give you a real number. It's just its length. So this quantity right here, a little difficult to squeeze in. Let me see if I can make that look a little bit better. There we go. This quantity right here is a scalar, right? And it is the reciprocal of the length of A. whatever the length of A is, if you multiply that by its reciprocal, you get 1. So by scaling A by that amount, we scale it to unit length. If A is longer than 1, its reciprocal is a fraction smaller than 1, and it scales A down to unit length. If A has a length smaller than 1, its reciprocal is greater than 1, so that's taking a very small vector and scaling it up to be a unit vector. Basically what we're doing, we often imagine unit vectors as giving us direction without having the sort of interference or pollution of a magnitude. So by scaling the magnitude to just 1, then when we do other things with that vector, as we'll see later on, that avoids other sorts of unintentional consequences and side effects. So we do a lot of this with unit vectors. The notation might be a little bit much right now if you're having difficulty following this. Just put that on the back burner for a moment, and maybe when you're a little more comfortable with vectors, it'll be a little bit easier to read what's going on there. But the idea behind it is just if we have a vector of any non-zero length, we can scale it to make a unit vector pointed in the same direction. This, of course, only works if A is non-zero for 2 reasons. One is algebraic. If A is the 0 vector, the magnitude of the 0 vector is 0, and you can't divide by 0. It doesn't make any sense. Also, the 0 vector does not have direction. It's just a point. So if you try to draw a unit vector, well, which way should the unit vector point? Who knows? There's no well-defined direction there. So that's why we can only do this with non-zero vectors. Okay. Now, one more piece, one more definition before I get into the sort of the meat of the central point of this video. And that is to list what we call the standard basis vectors. That is some terminology from linear algebra. Many of you, I'm sure, will be going on to study linear algebra. You'll run into this more. The idea is that, well, it's a little difficult to describe right now what a basis is. If you want to know, you can ask me later after you have worked through the material of this section and feel pretty comfortable with it. So we have standard basis vectors. These are unit vectors that are aligned with our coordinate system. So for instance, we have I, which because it's a unit vector, I'd write it as I hat. This is the unit vector in the positive x direction. Clean that up, that looks ugly. Positive x direction. And associated with this is a vector j. This is the unit vector in the positive y direction. Using sort of ditto marks there to just indicate that we're copying that. So I points in the positive x direction, j points in the positive y direction. If we're working in 3 dimensions, most of the drawings and examples we've talked about so far have been 2-dimensional, because that's easiest to put on a page or a screen. But we could be working in a 3-dimensional space, and if that's the case, then k would be the unit vector in the positive z direction. Okay. So in 2 dimensions, we would, in the usual orientation, we would have a vector I pointed to the right. Actually, you know what? Let me do a couple of things here. Well, first, keep forgetting, I just recently remembered, which is kind of silly, that there are easy ways to draw straight lines in this program, so that helps. Suppose we have x and y axes. Then the vector I would be the 1 unit vector pointed to the right from the origin along the x-axis. And the vector j would be the 1-unit vector pointed up from the origin along the y-axis. Those would be your I and j. If you're working in 3 dimensions, let's do something like, bring it down to there. There we go. Okay. So say we have an x-axis here, and a y-axis there, and a z-axis there, with 1-unit marks in each direction. This would be your vector I. So from the origin to 1 unit on the x-axis. From the origin to 1 unit on the y-axis would be your vector j. From the origin straight up 1 unit on the z-axis, that would be the vector k. So you have your I, j, and k. There are better pictures of these in the textbook. Should be easier to understand. So those are our standard basis vectors. These are the most common names for them, and the names used throughout the textbook. You will see other notations in other sources, so I'll just mention some of those briefly. One of them, especially in more general linear algebra contexts, we often use e's for the basis vectors. So E1, E2, and E3 would be the I, j, and k vectors respectively. This is the standard unit basis vector pointing in the first dimension, second dimension, third dimension. You might also see them given the labels of the variables. So E sub x, E sub y, E sub z. That's another sort of triad that you might run into. Or some sources even use x hat, y hat, and z hat. So these would be written as vectors, but with the hat notation. Now here's a case where the hat notation would be necessary to indicate unit vectors, because otherwise, we often use x as a vector in general. That doesn't have anything to do with the x-axis. It's just a variable. So you would need some way to indicate that you mean specifically, oh, no, the unit vector in the x direction. But because of that clash with other vectors, I don't really recommend using that. Just be aware of it because it does show up from time to time. I've seen it in the Wikipedia a couple of times, for instance, when I'm checking on some topic or another. I've seen that notation arise. So if you see something like that, that's probably what they're talking about. But our purposes in this class, we will exclusively use I, j, and k. Okay. So quick summary before I move on. This is probably going to be a long video. There's a lot to talk about here. Our goal, what we're moving towards, is figuring out a cleaner way of doing vector addition. And that's what we'll move to in a moment. We just needed to talk about what we need to be able to denote the magnitude or length of a vector. We have unit vectors that are length 1. Any non-zero vector we can scale to be unit in length, pointing in the same direction. And we have these standard basis vectors that align with our coordinate system. There's a certain sense in which you could say that the standard basis vectors define the coordinate system. If you start off by saying, okay, this is how I, j, and k point, well, that determines where your x, y, and z axes are, right? So that's kind of the basic idea there. Now, let's consider some sort of, how big do I need to make this? Let's do something like that, where we have y, and we have x, and let's see here. 3, let's say that's 3, and then we have 1 going this way, 1 going that way. These are probably not entirely precise. I'm just kind of eyeballing it. But, all right. So, suppose we have a vector that, okay, yeah, getting those strict diagonals is not going to work. So we'll just kind of, again, eyeball this. So suppose we have here a vector that I'm going to call u. At an angle of 45 degrees, pi over 4, off of the horizontal. And suppose that the length of u is the square root of 2. And now you can see why I put the end where it is. You know from trigonometry, this is a 45-degree angle, and this is square root of 2 units long. That means we were going right 1 and up 1, right? So we have that endpoint there located at 1, 1. Now suppose I come back here, and we'll draw another vector j coming out to about here. Not j, sorry. I was thinking ahead. V is what I meant. We'll get to j in a moment. Apologies. V. Okay. And V, I want to be at an angle of 120 degrees with a length of 2. Okay. So, if we sketch out what's going on here, we're going left 1, up radical 3 with a length of 2 right here. Here we have a length of radical 2 that we're obtaining by going right 1, up 1. All right, so these are some common triangles. You know what these lengths are, and you see what's going on here. Okay. Now, suppose that we want to add u plus v. Okay. We could do this with the triangle law or parallelogram law, right? Whichever way we approach this. This is kind of written for the parallelogram law, so let's kind of start making a parallelogram here. Okay, so extending the parallelogram, it looks like the sum u plus v will go from the origin up to somewhere around here. Okay. It might be on the y-axis, might be a little to one side or another. It's a little bit difficult to tell just by eyeballing it. But let's see if we can figure this out a little bit more precisely. Actually, let's move this vector length over here to free up a little bit of space here in case I need it. Not sure if I will, but, who knows. So let's look at this vector u. And remember that we have a vector I, the unit vector from the origin to the point 1, 0 on the x-axis. And there's a vector j coming from the origin up to the point 0, 1 on the y-axis. And looking at I and j, and again thinking about the parallelogram law, I plus j would give us u, wouldn't it? So the vector u is equal to the vector sum of I and j. It is the resultant of these two vectors, right? And if we want, we could write that as like 1i plus 1j. There's a list of vector properties in the textbook in this section, and it writes them all out in symbolic form, but that list of properties, I think it writes them out as 8 properties, somewhere around there, give or take. And they're basically saying that the operations of vector addition and scalar multiplication have the basic algebraic properties we would expect. Each of them is commutative, each of them is associative, the two together have a distributive law. The 0 vector is an additive identity, any vector plus 0 is itself. The scalar 1 is a multiplicative identity, any vector times 1 is itself. Okay? So that means we can write 1 times I, and that's just I. 1 times j is just j. So these are the same thing here. So in a certain sense, we have sort of broken apart the vector u into component vectors, I and j. We've sort of decomposed this vector into a sum of 2 other vectors. Well, let's do something similar with v. I've already drawn the triangles to illustrate what's happening here. V is kind of going in the opposite direction of I. Not directly opposite, but it's going to the left, whereas I goes to the right. But if we look at negative I, right, negative I is the vector that's the same length as I, but pointing in the opposite direction. So that goes this way. J goes up, and V goes up, but it's a little bit longer than J, right? We have this radical 3 here. If we draw the vector coming up that is of length radical 3 times J, so you see if we go left 1 unit and up radical 3 units, in other words, if we take the vector negative I and we add the vector radical 3j, I've drawn this here with the triangle law, that tells us that the vector sum, the resultant of that, is the vector v. Right? So we can decompose v as negative I plus radical 3j. Now, of course, notice that the endpoint of the vector u, when we start at the origin and end here, that endpoint has coordinates 1, 1. And this point here, where the vector v ends, has coordinates negative 1, radical 3, right? Again, from trigonometry or just right triangle geometry, or your special triangles, whatever, however you want to describe that. This point has points negative 1, radical 3. This point has coordinates 1, 1. And that translates into the coefficients that we have, the scalar multiples in front of I and j, right? Actually, we can make that a little bit clearer by pointing out that negative I is negative 1 times I. Right? So we have negative 1, radical 3. We have 1, 1. So if we want to consider the vector sum u plus j, I keep doing that. I don't know why. I'm sorry. U plus v. Well, the vector u is 1i plus 1j. The vector v is negative 1i plus radical 3j. Okay. Now, I mentioned that we have that list of properties that tells us that vector addition is commutative and associative. That means that we can drop the parentheses here, rearrange terms, and bring them back together so that we have 1i plus negative 1i, so minus 1i, plus 1j plus radical 3j. Right? And I mentioned again there's a distributive law, so that allows us to factor out that I and say that we have 1 minus 1 times I. I guess I will, it's weird to drop them after all this time. I'll put the serif back on that. 1 minus 1 times I plus 1 plus radical 3 times j. 1 minus 1 is 0, so we have 0i plus 1 plus radical 3j. And 0 has its algebraic property where the scalar 0 times a vector gives you the 0 vector. So this is the 0 vector plus 1 plus radical 3 times j. And again, the 0 vector is an additive identity, so 0 plus any vector is just that vector itself. And we are left with 1 plus radical 3 times j. So you note that this now is a vector that points in the direction of j and has a magnitude of 1 plus radical 3. Or was it approximately 2.7? A little over 2.7? Go ahead and let's do that. Let's say approximately equal to 2.7 j. And if we come back to our picture, this vector that we drew here, I tried to make it close, this is ballpark. If that's 1 and that's 2, that's 3, this could be around 2.7, right? There's our vector that is 1 plus radical 3 times j. Okay. So the idea here behind what I just did, this is a whole lot of writing. I was kind of illustrating the vector properties with some algebra here. Obviously, in practice, we don't write out every single step like this. I was just kind of pointing out along the way carefully like what the line of reasoning is at each step. But what we see is that if we take these vectors and decompose them as sums of vectors in the I direction and the j direction, in other words, horizontal vectors and vertical vectors, as scaled multiples of I and j, our standard basis vectors. If we rewrite them as sums and then rearrange how we add the vectors together, then the resulting vectors in I and j, the sum of those gives us, the original sum we were looking for. So, this is a very cluttered diagram now, so let me extract some of the key ideas. We had a vector u and a vector v. And we broke u apart into a vector that goes right 1 and up 1. And v is a vector that goes left 1 and up radical 3. So we have here, there's a vector that goes right, there's a vector that goes up, there's a vector that goes left, and there's another vector that goes up. So from the beginning to the end, we see that, by just rearranging these little vectors, we see, oh, we can just go up 1 plus the square root of 3 straight. The movement to the right and the movement to the left perfectly cancel each other out. Now I had special triangles here, but of course we can decompose these vectors using trigonometry, whatever the angles and lengths are, right? You can always figure out what your x direction and what your y direction are based on just the magnitude of the vector and using sine or cosine of your angle. So we can always take a vector and decompose it into horizontal and vertical components. And what this work over here kind of illustrates, it doesn't prove it, but it does sort of illustrate that we can then just add those respective components to get the vector sum we're looking for. This turns out to be extremely useful, and so useful we give it a shorthand notation that requires even less writing than the i's and j's and whatnot. So here's a definition here, somewhat lengthy. If the point P with coordinates a1, a2 in R2, so let me draw a quick little illustration. So suppose we're in R2 and we have x and y, and we have some point that we'll call P, and this has coordinates a1, a2. Here's our origin down here. So let's use that as the initial point of a vector, and we'll let the terminal point of a vector be the point P itself. Okay. So P is the terminal point of a vector whose initial point is the origin. We call that vector OP. That uses the kind of the ray notation from from Euclidean geometry. So this vector is the vector from O, the origin, to P, our point. This vector is then called the position vector of P. And we can write OP as A1 times I plus A2 times J. This is the style of thing that we did. Let me pop right back to that. Here I wrote U as 1I plus 1J, and I wrote V as negative 1I plus negative 3J. That's because the coordinates of U are 1, 1, coordinates of V were negative 1, radical 3. Okay, so, wherever I is, I don't know if A1 is bigger or smaller than 1, but let's suppose it's bigger, so maybe I is here. Then this vector here would be A1 times I. Right? A1 is a scalar multiple scaling the unit vector I, so we get that. Similarly, A2 times J, if this is J, then this would be A2 times J. And when we add A1I plus A2J, This parallelogram law tells us that we get the vector OP. This notation is so useful that we have a shorthand where we put A1 and A2, the component, kind of the lengths of those components, which are also the coordinates of the point P, between these angle brackets. Okay. We say that those scalars A1 and A2 are the coordinates of the point P, and they are the components of the vector OP. And so, to draw an analogy, again, flipping back, -1 radical 3, those are the coordinates of this point in the plane, and -1 and radical 3 are the components of the vector V. Okay? With -1 being the horizontal component, and radical 3 being the vertical component. Okay. So this, like I said, this is so common that we will often just strip out the i's and j's and the plus sign and make it a little bit more compact and write this much like we do ordered pairs, except using angle brackets to indicate, hey, this is actually a vector we're talking about, which implies a certain sort of displacement or movement or something like that, just to keep things separate. So now we have we have these nice shorthand ways of writing these vectors. And we have, this allows us to give symbolic definitions of these vector operations as opposed to relying on vectors for everything we do. Diagrams, like pictures, right? So say we have one point and we want to add a couple of vectors. We have a vector A and a vector B, right? And we want to add A plus B. Well, if A has components A1 and A2, and B has components B1 and B2, and C is any real number, then A plus B will be a vector whose first component is the sum of A1 and B1, as A1 tells you how far A goes left to right, B1 tells you how far B goes left to right, so the total amount you go left to right is A1 plus B1. And the second component, the vertical component of this vector sum, is A2 plus B2. A2 was the vertical component of A, so here it's going up. B2 is the vertical component of B, which now is negative, so that's coming down slightly, and when you add those together, you find out the net distance you went up. So A1 plus B1 tells you how far you go right, A2 plus B2 tells you how far you go up. Those are the horizontal and vertical components that describe the vector sum of A plus B. So just kind of adding the x coordinates, adding the y coordinates is basically what we're doing. The vector difference, A minus B, it's just the difference of the respective coordinates. If you want to scale a vector, so here's A with components A1 and A2. If you multiply that by some constant C, maybe C is 2, so you double its length. Well, then you're just doubling how far right you go and how far up you go. So you just double each component individually. So C times a vector A is just C times its first component, C times the second component. Everything works out fine there. And the vector magnitude, of course, can be easily computed with Pythagorean theorem. When A1 and A2 are the directions you go left and right respectively, we've talked about how we find distances. We can just, use Pythagorean theorem there to find out how long the vector A is. So everything that we gave a visual and geometric description for previously, with the notion of decomposing vectors with the aid of the standard basis vectors, we are now able to do quite a lot just symbolically. And in a two-dimensional vector space, we see actually that the vector I can be written with components 1, 0, and j with components 0, 1. And there are two ways to see this. One is to use this notion of how we defined this. These components refer to the coordinates of the terminal point P. Well, if you put I in its standard position with the initial point at the origin, its terminal point is at 1, 0, right? That is x1, y0. So its terminal point is 1, 0. So that means that its vector components are 1, 0. J ends at 0, 1, so its components are 0, 1. Or we could use this definition here, where we say that, okay, vector components 1, 0 translates into 1i plus 0j. But 1i is just I, 0j is the 0 vector, I plus the 0 vector is I, so component, the vector with components 1, 0 reduces to just the vector I. And similarly, you expand that for j, and suppose I can write it out, it won't take long. Components 0, 1 means 0i plus 1j, and that reduces to just j. And so we have these nice clean representations of these vectors. In a three-dimensional vector space, I don't remember at what point the textbook introduces these, hopefully it's brought them up. V sub 2 represents the two-dimensional vector space that corresponds to R2. V sub 3 represents the three-dimensional vector space corresponding to R3. Now we have the I, J, and K, and those are of course the respective coordinates in the 3 space here, right? So if we have our x, y, and z axes with I, J, and K, well, I is located at 1, 0, 0, J is located at 0, 1, 0, K is located at 0, 0, 1. So using the coordinates of the terminal points, we can translate those into component form. Or again, we could translate each of these. I won't do this for all of them, but let's just do for I, for instance. We're claiming something about this vector here. Well, 1, 0, 0, we can define, now this is 3 components, and this definition I gave above only has 2, but we can extend this to R3. We can take a point P with coordinates A1, A2, A3 in R3, and then the vector OP would be A1I plus A2J plus A3K, and have components A1, A2, and A3. And so that's what we have here. 1, 0, 0 would represent 1I plus 0J plus 0K, and 1I is I, 0j is the 0 vector, 0k is the 0 vector, and I plus the 0 vector plus the 0 vector is just I. You can do similarly for j and k. All right, so we get these nice little representations here. Let's finish up with one quick example in a three-dimensional setting to work this out a little bit. So we'll let A be the vector 2i minus 4j plus 4k, and B be the vector 2j minus k. We are asked to find 2a plus 3b and the length of A. So let's focus on the first one first. We have 2a plus 3b. Let me first do this just algebraically. So we have 2 times the vector 2i minus 4j plus 4k plus 3 times b, and b is defined to be 2j minus k. So what we'll often do in a case like this is treat I, J, and K as formal symbols, as if they were variables, or, well, they are constants, just say constants, and just work with this algebraically. Distributing the 2, we get 4i minus 8j plus 8k. Distribute the 3, we have plus 6j minus 3k. Collect like terms. We have 4i. I don't see any other i's, so we have 4i. Minus 8j plus 6j. Combining those terms, that leaves us a net minus 2j. And we have plus 8k minus 3k. That leaves us plus 5k. And it looks like that linear combination of 2 times a plus 3 times b gives us the vector 4i minus 2j plus 5k. There is a slightly more compact way of writing this if we wish. And that is to say, all right, so we have 2 times the vector a. Let's write a in component form. Its I component is 2, its j component is -4, its k component is 4. We have 3 times the vector b. Let's write that in component form. Sorry, gotta pay attention. There is no I, so the I component is 0. The j component is 2, and the k component is -1. So this between angle brackets here is another way of writing the vector a. This between angle brackets here is another way of writing the vector b. And if you check back to our vector definitions we gave just a moment ago, let me scroll this back up. A scalar multiple of a vector, you just scale each component by that value. So 2 times this vector is going to be the vector 4, -8, 8, just multiplying each one there, plus 3 times this vector, 3 times 0 is 0, 3 times 2 is 6, 3 times -1 is -3. So we have that. I'm going to write a step here that I wouldn't normally, just to illustrate. To add these two, we can now just add the respective components. So it's 4 plus 0, -8 plus 6, 8 plus -3. And then when we combine and simplify that, we have 4, -2, 5. Four, -2, 5 inside of angle brackets is another way of writing the vector 4i minus 2j plus 5k. So when you see something like 4i minus 2j plus 5k, there are 2 equivalent ways to think about this. You could think of I, j, and k as just kind of formal symbols indicating the 3 components, 4, -2, and 5. Or you could think of, okay, 4i is a vector that's 4 units long pointing in the positive x direction. -2j is a vector 2 units long pointed in the negative y direction. 5k is a vector 5 units long pointed in the positive z direction. And what vector would you get when you add those 3 together? So there's that geometric interpretation, or like I say, there's just the formal interpretation where you treat that as being equivalent to this down here, and just have those respective components, whichever way you want to think about it. Yeah, so these two are equivalent. Almost any problem where you see one form written, you can switch to the other if you prefer it. Some people prefer ij's and k's. Some people prefer the angle brackets. There are some situations where I favor ij and k myself. I typically default to angle brackets because it's compact and mathematicians are lazy. So I like to write as little as possible. But there are places where ij's and k's are more useful, so I will use those from time to time. Frequently in a given problem from the textbook, I will try to stick to the form that's given unless I have a reason to switch to the other. The textbook uses both versions, both notations here, although it feels to me like, especially later on, it uses ij's and k's more common than the angle brackets, so later in the course I will more commonly take an ijk and convert it back to this if I'm having to do a lot of writing. But both are good. Make sure that you can read and write both notations. They are both important. Let me finish off this example with, it asks for the magnitude of the vector A. So the magnitude of A, I will just write that as the magnitude of this compact version here. We have 2, -4, 4. So that is the square root. Oh, I want that. There we go. The square root of, let's use parentheses at first here for symmetry, 2 squared plus -4 squared plus +4 squared. And that is the square root of 2 squared is 4, -4 squared is 16, +4 squared is 16, 32, 36. Oh, that's convenient. We have the square root of 36, and that equals 6. So it turns out that that particular vector A that we started with happens to have a magnitude of 6. I often ask you to show work for written assignments, and it's an important skill to be able to document what you're doing. The key thing there is making it very clear to a reader what you're doing and how you got your numbers, right? So, for example, if you're confident in your arithmetic and the vector A is printed out, it would be okay to just say, all right, well, if we're to know what the components of A are, you can square those respective components. And if you do the mental math and realize that, oh, that's square root of 36, which is a square number, that's obviously 6, this is an acceptable way, as far as I'm concerned, to write this thing out. That is sufficient work for it to be clear that you didn't just guess, oh, I think it's 6 units long. No, it's clear that you know how to find the how to find that length. So one purpose of you writing your work is to convince your instructor or grader. In this case, that's me, but you'll have other classes and whatnot. You have to make sure to be able to convince a skeptical grader that yes, you do understand how to do this work. There's the practical purpose of, again, we're trying to teach you how to communicate in mathematics. So out in the real world, you will often be on a team of people, or even if you work alone, you will often have somebody to report to or to share results with, either a boss or a colleague or something. So you need to be able to justify your work. Somebody needs to be able to look and not just say, wait, how do we get this? And how much justification is necessary depends on the level you're working with, or working at, I should say. Obviously, in a future setting where all of your colleagues have the same level of education as you do, you would probably be able to just say, oh, the magnitude of A is 6, and leave it at that. They can figure it out and check it on their own. But if you have a non-technical, if you have a manager who's a little bit less technical, maybe you need to show a little bit more work so that either they can follow along and be convinced, or they can at least trust that, okay, well, there's a reason for this. If I show this to somebody else, they'll be able to figure out what's going on. A good rule of thumb when trying to figure out how much work you need to show is to imagine that you are working with a classmate of yours who has about average or slightly below average understanding of the material. So like they have read the things, that they've been doing the same work that you have, so you don't have to define everything from scratch. You can assume that they're in the same general context as you, but they might need a little bit of explanation to follow along, right? So if you're in a situation where you're kind of struggling a little bit, writing down as much as you need to work things out will probably be sufficient. If you feel that things are coming pretty easily to you, maybe throw in an extra step or two just so that, maybe one of your peers would be able to read your work and say, oh, okay, I that makes sense. I see what's happening there. And that's kind of a good rule of thumb as to how much work you want to include. Now, kind of been spending a lot of time. Oh, so as another example, I think I mentioned this in passing, but I didn't remark on it explicitly. I mentioned when I was writing it that I wouldn't normally write this step right here. This step right here, I wrote down so that you can follow along and see where these numbers are coming from. Once you have practiced with these, you will probably, from an expression like this one, you will probably just skip straight to this answer, right? You would mentally say, okay, 4 plus 0 is 4, -8 plus 6 is -2, 8 plus -3 is 5. That should be pretty transparent what's happening there. Once you've, if it's not transparent right now, once you've practiced and done some exercises, you'll get the hang of this, and that should be a bit clearer. So this is another example of a step you might skip. Some of you might be thinking, okay, well, this is kind of obvious. Like, of course we're going to add the components. What else would we do, right? Why would we spend all of this time with this like A1 plus B1 kind of business? Like, what else would we do here? But this is not actually as obvious as it might appear to some of you. It is a very special characteristic of the shape of Euclidean space. So let me give two examples. Let's think about velocities. Suppose you are on a vehicle of some sort, and that vehicle is traveling at 20 miles per hour. And while you are traveling, you throw an object forward with a speed of 50 miles per hour relative to you. An outside observer would observe that object then moving at 70 miles per hour, right? The speed of the vehicle plus the relative thrown speed, 20 plus 50 gives us 70 miles per hour. And this is what we call Galilean relativity. It allows us to shift between different coordinate systems. Okay. But now suppose that you are on a vehicle traveling through space at, let's say, 200 million meters per second. I hope I'm remembering the numbers correctly. If I have made a gross error, make the appropriate adjustments. And you fire a projectile forward at 100 million meters per second. This Galilean relativity principle would have us, would say that an outside observer would observe that projectile moving at 300 million meters per second. However, if I have recalled my figures correctly, 300 million meters per second is slightly more than the speed of light. There is no way for an observer to see an object moving that fast. In fact, the velocity vectors, these two velocity vectors would sum to a velocity vector whose magnitude was a bit less than 300 million meters per second. In Einsteinian relativity, the addition of velocity vectors is much more complicated than in the Euclidean Galilean sense. We can't just add the components, it doesn't work. Now, if relativity is a little bit too abstract, let's consider something simpler like displacement. Suppose you are standing someplace and you travel 1 mile south, and then you turn 90 degrees and you travel 1 mile east, and then you turn left 90 degrees again, and you travel 1 mile north. Okay. If you do that, your net displacement your net displacement, you can see, is 1 mile east, right? You end up in the same spot you would have if you had just gone 1 mile east from your starting position. And this is because on small scales like this, we can imagine the surface of the Earth as being approximately flat, approximately a Euclidean plane. But of course, the surface of the Earth is not a flat Euclidean plane. If you are at the North Pole and you travel, I don't know, 500 miles south, and then you turn 90 degrees to the left and you travel 500 miles east along that line of latitude, and then you turn 90 degrees left and travel 500 miles north, it will feel to you locally like you have done the same series of actions here, except now, after that path, you will find yourself right back where you started, and your net displacement will be the zero vector, because the surface of the Earth is the surface of a approximately spherical shape, which is a non-Euclidean geometry. Okay, so for large-scale navigation, if you're trying to talk about like the flight path of an international flight path for of an airplane, or if you're trying to talk about like shipping cargo across an ocean, well, now you can't just add velocity or position vectors in this case. Here we're talking about position or displacement. You can't just add spatial vectors as Euclidean objects with add the components. It just doesn't work anymore. So actually, these definitions that we have are very simple, and they're very clean, and they're very nice, and they're special features of the Euclidean space we're working in. So try to be appreciative of these facts. In different scenarios, vector mathematics is much more complicated. But in this course, don't worry, in this course we will keep things simple, and everything will just kind of work out in these natural ways. But think carefully about what you're doing and make sure that you understand, that these are, why these operations are justified. Don't just add components because we're adding vectors. Remember the fact that, when we add these vectors in a nice flat Euclidean space, they just combine in this nice natural way, and everything works out there. Okay. This video has probably gone on way too long. I was not looking at the time count there. Hopefully you're still with me and understanding. If you have to take this in shifts, hopefully you have done so and managed your time accordingly. But my hope is that this clarifies some of the material and at least the justifications of why we work with things in the way that we do in this section.